All right, so today we'll be going through network virtualization. We'll have a look at cloud computing and how that's changing the world of networking. And then we'll discuss the importance of virtualization, looking at how we integrate this into network design and infrastructure. We'll give you a brief overview of the new software-defined networking and look at the various controllers that we use in network programming. So this is a rather new area within the world of networking. So there's a video with the online material that covers data centers, cloud computing, and virtualization using hypervisors. But we'll start off going through the wall of text. So cloud computing, I mean, we've probably covered this in other units, because I know I just recently finished a unit for the Bendigo class on virtualized servers. So probably should have covered all of this anyway, but let's do a recap. So cloud computing allows us to access our applications and data from anywhere at any time. So we subscribe to the services that we require, and this allows us to streamline operations. Minimizes the IT infrastructure, maintenance and management as far as our own internal IT department goes. We don't have a massive overhead outlay when we need to stand up new equipment. We don't need to necessarily have a big outlay in plant equipment or training for the new equipment. And it allows us to rapidly respond to changing business requirements, such as increased volumes in data traffic or storage, or even standing up new solutions. So we can look at this as software as a service, where we basically get our applications and services, or we can have it as a platform where development tools and services are used over the applications. This allows us to provide a different level of service to our customers. And the last one is the full infrastructure as a service, where our provider provides all of our services under a managed agreement. So everything's virtualized and supported. Now, depending on what we need, we can have one or another, or a combination of these things. It comes down to how we negotiate the contract to support what we need. And all of this comes under a contract agreement with our cloud service provider. And what we've got to take into account, as always, is the mix and match approach of how we want services to be provided. So we can have public clouds, which are available to everyone, private clouds, which applications as services are only delivered to an organization. You can have a hybrid mix of the two. So you take elements from the public and the private clouds and set it up so it's customized to your requirements. And that's the most common solution that is implemented. Because a lot of solutions are needing the privacy of like your HR department and that. You don't want that to be out mixing where other organisations are accessing the same services and things like that. You want it kept private and only your organisation having use of those services. Community clouds are modelled for exclusive use within a specific group, and they meet the functional needs of that community. So, like healthcare is a very common example they use throughout the course, and there's big strides in sharing resources throughout the healthcare industry, but they need to remain compliant to the appropriate policies and laws that apply to that community. So where do you run this cloud computing? Well, you can have your traditional data center type setup where storage and processing is in-house to the IT department, but it's fairly expensive to build and maintain. Cloud computing offers all the benefits of having this, but at a fraction of the cost. And the benefit of provisioning and releasing all of this with very minimal overhead cost to the organisation. So cloud service providers use their own data centers to host their services, and they will do their load balancing on all those sorts of requirements throughout their own infrastructure as they need. So all what you need to do is scope what you want correctly, and it's all provided to you. You don't have to worry about finding physical locations, making sure you've got power and cooling and all the other bits and bobs, security, getting it staffed and maintained. So cloud computing is a very easy, low-cost alternative. So virtualization. Cloud computing and virtualization are basically the same thing. All right. So cloud computing is providing a service via virtual, whereas virtualization, you can just say it's just a way of accessing or maximizing your return on investment on your physical hardware. Now, a lot of industries have already gone to virtualized hardware solutions, and that they're making maximum use of their hardware because they put a lot of money and time into buying and setting up this hardware. So by adding the virtualization features over the top of it and running multiple server features on the platforms, they are maximizing their return on their investments. So why is cloud computing and virtualization basically interchangeable? Well, because virtualization is the foundation of cloud computing. If we didn't have virtualization, we wouldn't have had cloud computing develop. So historically, we had dedicated servers providing different features, and we didn't tend to mix the features very much. We did this because sometimes running multiple services on the one server caused issues. And if you lost one server, you would end up losing quite a bit of services across your network. Now, as things have become more critical, you know, server sprawl, companies being more cost aware, and they're willing to take the risk factors of having combined services. And the beautiful thing with virtualization is we can set them up so that we basically have replicated services. So even within the same hardware infrastructure, we can virtualize them and have failover between the existing hardware so that they're basically complete mirrors of each other, and we have inbuilt redundancy even on the hardware we have. So this provided greater security with very little further investment on behalf of the companies. So this allowed us to run multiple operating systems and multiple server functions on the same amount of hardware. So this allowed us to provide greater flexibility with little to no extra cost on top of the expenditure that we already spent on the hardware. So the major advantages of virtualization was cost savings. We had less equipment requirements, less energy being consumed, didn't need as much space. We could get rid of our older servers without impacting services. It became a win-win situation as far as business was concerned. We could also prototype and test services very quickly and easily. We could provision new services fast. We established greater uptimes. We had much easier implementation of disaster recovery, because with vSphere, for example, it was very easy to get that redundancy built in to our virtualized solution and have the redundancy and failover inbuilt into our virtual circuits. And most of it, it didn't matter what version of operating systems and whatever we were running, it could all be ported across to the virtualized solution. So instead of having multiple repeated functions, we could use common hardware, firmware, and then use a hypervisor to manage how all of the resources are allocated for our various operating systems. Previously, it was only a single operating system consuming all the resources of the server. Now we can maximize it so we can take better load balancing considerations. So if a server is underutilized, we can load it up with other virtual machines and make the efficiency or utilization factors increase. So we're getting a better return on investment. So hypervisors, there's two types. Hypervisor type 2 basically allows us to run and create VM instances. Now, these are normally known as host solutions, because we use them as endpoint devices, and we have an underlying operating system underneath the hypervisor. Whereas type 1s, the hypervisor is basically the operating system, as we can see here. So these are also referred to as bare metal approach, which means we have the hardware, we load the hypervisor software on, this replaces the operating system, and then we can load our virtual instances on top of it and have them accessing the resources directly via the hypervisor. This improves scalability, performance, and overall robustness of the solution, as we're not reliant on the underlying operating system as we are with type 2s. Right, so type 1s still require a management console, and this manages the hypervisor. The console allows us to recover from hardware failure, and it can automatically move our virtual machines to other servers using such solutions as unified computing systems, managers, VM Sphere allows us to do this as well. So there's lots of different vendors that provide these type 1 solutions. The main thing is that we need to ensure that we have the resources available to allocate to the virtual machines. Remember that most of the time, the hosted operating systems very rarely require allocated resources. So when they're running, their actual utilization rate might be quite small. So we can stack them up and duplicate these instances and maximize utilization and make everything more efficient. So the virtualization hides server resources overall. Now, this would be a problem under traditional architectures, but virtual machines are movable, and it allows network administrators to add, drop, and change networking and resource profiles to support requirements as needed. The traffic flows between these virtual instances are different from traditional client-server models, because traffic can be exchanged between different servers and may need to be bridged across quickly between the various solutions. So this is known as east-west traffic, so going between the servers, and north-south traffic is where it's coming in and out of the site, such as other cloud providers, the internet, or other locations. So we need to have a dynamic solution that allows for the changes in this network pattern, and we need to support quality of service and have a robust security solution in place. All right, so You might not have the same vendor across all your solutions, but you need to be able to configure your systems to make them as efficient as possible, because reconfiguration can be time consuming. So network infrastructure can benefit from virtualization, as just about all functions of a network can be virtualized. Excuse me. We have a high pollen count over here today, so my hay fever is playing up. So examples of what we can do is virtual devices can operate independent devices. So we can via software-defined virtual devices and make them service elements. We can virtualize routing and forwarding, and we've looked at this. We've done VLANs, we've done routing tables. Now we can do VRS, which are virtual routing tables and forwarding, which create a virtual router inside a router, for instance. And I've done this on multiple occasions, especially in labs where we need to simulate high volumes of traffic and segregate them from each other so that we can generate a testing environment doing different things without impacting each other. So we can have different routing protocols that can't see each other, doing different routes, and maximize the use of hardware. This is very good for when we need to test our robustness of our solutions before putting it in production. So next is our software-defined networking, and we have a little video on the curriculum there that will help you understand programming networks, defining the software-defined networking via Open Network Foundation, OpenFlow, or OpenStack, and look at the various controllers. So what you need to understand is we've got two planes in routing. One's a control plane. This is where the decisions are made. So they're the ones that are where we have our routing tables and make our forwarding decisions and that sort of thing. The data plane is our forwarding plane. This is where the packets come in and get shunted in and out of interfaces. Okay, so this is where all of our data that we're transporting gets moved around in. We don't necessarily need to lift the packets up into the control plane all the time, and we've discussed express forwarding and things like that. So you've got a brief understanding of what we're talking about here in previous chapters. So the idea with express forwarding is to enable us to bring predefined forwarding decisions down into the data plane, and by having software defined segregation, we can control the functions and have the controllers bring that decision down into the data plane to increase data flow, security, and any other services down in the data plane. Because every time we move out of the data plane up in the control plane and back down, we're adding delays. So by having this centralized controller, controlling communication and bringing the decisions down into the data plane for us, we minimize the delay added by going through this device. Now, if you remember, the way the express forwarding worked was it did a pre-calculation of all the possible routes known from its routing table, its forwarding table. So it calculated all the combinations and then brought those combinations out of the control plane into the data plane, and the data was expedited along those predefined paths. So now we have an extra one, the management plane. So this is used for managing the devices, and we use that by SSH and the usual suspects. So we can use file transfers, secure HTTP, if we've got a web interface, so on and so forth. So this allows us to do the management of our devices using SNMP, for example. This is where those items communicate and gain access to features. So what we want to do is use the software tools to define the architecture in a virtualized network. This allows us to have a brand new approach in the management and administration of networking. The idea behind it is to streamline the administrative process. So we basically get onto a management console, define the changes we want, and it pushes it out. The Cisco application infrastructure is Cisco's purpose-built hardware solution for integrating clouding, computing into data center management. So what we're basically looking at is a new way of automating and controlling our infrastructure. Now, this has required an introduction of brand new technologies and features throughout the network. Remember how I talked about yesterday the Marquee software-defined switches, that we could virtualize the switching across hardware that wasn't stacked? That's what we're talking about here with software-defined networking. So OpenFlow was developed by Stanford University to manage traffic, and it is a protocol that allows us to do and build software-defined solutions. OpenStack is a different way of approaching it, and this allows us to scale cloud environments and provide infrastructure as a solution. This can and often is used with Cisco's ACI in the data centers, and allows us to automate a lot of the provisioning of components within that infrastructure. Now, there is many different components of software-defined networking, and realistically it's a course and research and deployment learning curve all on its own, because you've got to take all of your elements that you learn about physical hardware and relearn how to define them in a virtual environment with all sorts of new protocols and technologies that you've got to get your head around to do it correctly. Just saying. So how does our OpenFlow type solution compare to traditional hardware architecture? So all our devices had individual control planes in them. With software-defined networking, we take that control plane out of the individual devices and lift it up into the controllers. So what is the purpose of this? Well, it allows us to control routing, traffic engineering, and mobility from a central location and push it out to all our routers and switches within our infrastructure. And our application layers, so our interfaces, are defined by apps, right? So business applications as well as software-defined applications. So network automation, software, it all gets integrated. And that's what is accessing the control plane on our behalf and then pushing out to the physical individual devices. And we have northbound and southbound APIs defining these interface points. So the northbound is where we're talking about the application layers interfacing with our controllers, and southbound is where the controller is interfacing with the individual devices in the data plane. We have two-way communications between each of those APIs. So how does this work in the world? Well, the controller defines the flow of data and it's centralized so that we can have information pushed out to all devices at once or individual devices as our requirements require. So each flow of traffic needs to get permission from a controller. So this enables us to have unified policies across our entire infrastructure and allows us to administrate our entire network from one source. So we only need to make changes to policies, and those policies on the controller will then flow out to all of our devices as the controller gives the communication permissions to flow traffic throughout the group. This allows for a very quick and unified approach to our entire infrastructure. Now, what makes up the ability to have this happen? Well, we've got a flow table. This matches incoming packets to particular flows and then assigns the function to be performed on those packets. Group tables are how we direct flow via a group, which can trigger a variety of actions that need to be applied to one or more flows of traffic. And our meter tables are where we keep track of the overall volume of traffic going via particular interfaces, whatever, and we can apply our rate limiting on traffic. So this is where we can do that lovely placing and color, shaping of traffic. So we can control our peaks and troughs via the meter table. So instead of doing this on an individual basis, we've come up with new tools that allows us to do it from a central location and control it by the controllers. Now, the benefits of this is, as I said, we've got one point of contact as far as applying policies. So we use the same interface point to set up all of our configuration, and we go back to that point when we need to modify it. So we can easily replicate any policy we need throughout the entire network instead of going to each individual location and retyping it in. We can just put it in on one location and then tell it where to apply it. It's much easier. And there's a video on the controllers and what they're doing. Enjoy the video as you go through the curriculum. So what are the three main core components of an ACI? We have the application network profile, which is basically a collection of endpoints and the policies that define the connections. Then you have the policy infrastructure controller, which is the centralized software that manages and makes everything scalable. It's the one that translates our application policies into network programming. And we use the Nexus 9000 series of switches that are application aware. All right, so if you remember yesterday when we went through the switching features and components between branch and service provider enterprise. So horses for courses, if you remember yesterday's presentation. So how does this work? We have all of our devices linked by the APIC, and we can then define the customer or the tenant contract, and this will then push out to the appropriate VLANs, any VMware installations, web services, applications and databases all get controlled. So we've got timing, alarms, clocking, access control, user control, all pushed out to manage. So this allows us to control all the devices. Okay, so these allow us to do this over a large network environment with high volume traffic, and allows us to scale it up as needed. We don't manipulate the data path directly. We basically define policies and allow the switches to make forwarding decisions based on those defined policies. So we're still allowing individual devices some leeway in that they can still adjust to local traffic conditions, congestions, so on. But they're applying common policies that are pushed down via the ACI fabric. So what does this mean? It means we're using applications to program the individual devices running within the network. So we can do it directly from the applications, or we can do it via many applications interfacing via a controller that then spreads it out into the individual devices. This allows us to have more options and more controls over the features and policies that we're imposing. And it allows us to define policy, and it allows us to automate the programmability of the devices via a GUI. So the individual administrator doesn't need to know exactly how to configure every single device in the network. All what they need to know and understand is how to drive the GUI, to define the policies that will then push them out in the appropriate manner down to the devices. So this allows us a dumbing down of the workforce, if you like. It allows us to remove specializations out of the workforce, which means there's less training required, and the enterprise spends their money on the infrastructure and the automation of that infrastructure, and then they don't need to constantly be retraining people in specialist fields for them to lose that knowledge as the staff turnover and attrition occurs. So the APIC provides single interface for management, so it will discover and populate the devices in the topology. It allows tracing of the paths between endpoints, and we can set policies through this interface. And you can delve down using the tools. So we can use this to examine every device in the network. You can see where ACLs are applied along the path, and you can see the effect that is happening as it's being applied. So the constant monitoring of the traffic flows and the configuration items are all being reported back into one place. And if you're trying to fine tune your traffic flows, you can see the instant results of your changes via the same tool. Okay, whereas before you'd go in, make changes to the ACLs, and then come out to a different tool to see what the impact of that has done, and you'd be chopping and changing, and generally there'd be big delays between the various applications getting updates. So please do the activities as you go through the chapter. And in summary, we had a look at the benefits of cloud computing and virtualization within the networking environment. We had a brief overview again of what SAS, PAS, and ICE is. We looked at the fact that we could have public, private, and hybrid and community clouds. We looked at Type 1 and Type 2 solutions for virtual machines and how those hypervisors differ in that one's basically used for end devices such as and is known as host virtual machines, where they run on top of an underlying operating system. And Type 1 hypervisors are bare metal. The hypervisor takes place of the host operating system. So it becomes the de facto operating system for the server. It then allocates resources to its virtual machines as required. So there are more efficient use of resources being allocated via the Type 1 hypervisor. We then had a look at new terminology for defining the type of traffic flows. So east-west traffic and north-south traffic between the application and the controllers and the end devices. So we had the ability to define how the traffic patterns change in a software-defined network compared to traditional networks. And we had a look at some of the different solutions that can be used in software-defined networking. And we looked at the separation of the control and data planes from the individual device and putting that control plane up into a dedicated controller that allows us to essentially manage our network and apply policies and configuration changes as needed across the entire network. This allows for greater flexibility and automation, and changes in hardware to support this solution is also required. We looked at the new fabric using this Nexus 9000 series of switches, which, let's face it, they're not going to be across the board in most enterprises anytime soon. So they're higher level machines, and they take the ability of having multiple subscribers or clients, tenants, having being segregated throughout the infrastructure and providing that security of information for each tenant and applying the policies and configurations throughout the network and allocating their resources as defined under the contract. That basically brings us to the end of the chapter, as that's the next slide. Now, as I said, software-defined networking is a very large and complex area of networking. It requires us to learn a brand new approach to how we lay out infrastructure and a brand new set of tools compared to traditional networking. So this module is only here to give you an introduction into the area so that you can then peer off onto your own research tangent if you want to get into understanding how virtualization and software-defined networking work moving into the future. It's not going to be in every single enterprise anytime soon, this really will take hold in service providers at first, then it'll come into large enterprise, then eventually it will trickle down to medium-sized enterprises as well. But that's a ways off, so this is why we're only introducing the topic here for you to get an understanding that it exists and to explore options if you wish to specialize within this environment. So you now have some reading to do, and I'll leave you be for you to go off and do that. I'll check back in just after 11 to see how you're going. I'm available via WeChat in the meantime or via email. All right. Any questions before we break off to self-study?